Okay, let's get started. For today's class, we will continue play with this magic mathematics stuff. So every Monday and Wednesday evening is a time for your brain movement to practice, have some brain training. Okay, so now let's start with a little bit review of what we have learned in last week. Okay, so last week we learned the predicate, which is kind of the extension of the propositional calculus. It's predicate calculus. Okay, and we learned two modifier. I want you to remember those things. Two modifiers, right? One is the kind of the reversed E. One is the upside down A. Okay, still remember those? Okay, so if you remember, let's see, what is this? Let's translate this expression into natural language. That's what we did. That's the very last question we did in last lecture. Okay, translate that into natural language. How can we do this?
For all programs in memory P, can all suspended programs,
Yeah.
then for all processors. Okay, so for all programs in memory that are suspended,
Yeah.
all processors will be idle.
Yeah, we can say something like this. Does it make sense? Does it make sense? So for our program in memory suspended, the processor is idle. It's not. It's yeah. I know the idea is there, something like that. But if we want to organize it better, to make more sense, it's because here it's a kind of implication. So if, then, okay. Before that is if. After that what happened. Okay, so if all the programs in memory are suspended, then all the processors are idle. Does that make more sense? Right? So if all the programs in the memory are suspended, because here if we only see this part, the first line here, all the P, which is programs in the memory, the P's program state is suspended. Okay, so that's what it means for this expression. But if we have this implication here, we put an if in front of that meaning. So if all the program in the memory is suspended, then all the processors are idle. Okay, so that's a upside down A, which means every element. Okay, another thing is the E. Let's see. This is how we translate it. We did that before. Let's see, can we do it again? One of the actuators will be functioning provided that system ambient temperature is within safety limits and the main reactor is not in a warm-up state. The current safety limits are 10 to 100 degrees. Translate that. We did that last time, and a lot of you made it. One of them will be functioning provided that. Which implies there is an implication there. Okay. If something happened, then something else happened. Okay. So here, after this provided that, after that, it's the condition, and before the provided that is something as a result. Okay. Alright. Okay, here's the solution. Like I mentioned, after provided is something as a condition. So ambient temperature greater or equal to 10, or and greater and less or equal to 100, and the main reactor's state is warm up, but we put a negation there. It's not warm up. Then what happens is one of the actuators, one of the actuators, which implies we should use the reversed E, because there exists a, we use exists. So this is A is functioning. One of the actors is functioning. So yeah, I want you to remember. So they have different solutions that depends on how much you practice those. You can quickly translate them into this calculus. However, here important thing you want to remember is what the meaning of this E and this A, those two modifiers, the reversed E, upside down A. So E means there exists a, and like one of them, yeah, at least one of them. If there's two of them, still we can use this E. But this A, kind of like or, E like exists, A like or. Okay, so this A is more strict. You want all of them to meet some condition, then you use this or. Right? Okay, well, that's something you want to remember, and we will start with today's game. Okay, so we will learn something, we'll talk about something like relations, okay? Okay, it's gonna be great. So I hope you still remember those basic knowledge of the set, because we will use a lot of them. I hope you. There's no time for me to review it again, so I think you should be able to remember all of them, because we were using that a lot of times, and we talked that for one lecture or two. So I won't repeat them again here to save some time. So relation. What is a relation? Yeah. What is a relation? You define a little bit. In general, what is a relation? Not here. What do you think is a relation?
Common association.
Yeah, something like.
Between any two elements.
Yeah, some sort of a connection between two things, right? Between two things. I mean, a pair. Okay. It can be a relation of one to many, something like that. But here, let's start talking about the relation, the connection between the thing, the two objects. Two person. It can be, yeah, relations, boyfriend, girlfriend. That's kind of relation, and student, teacher, yeah, relation. But here, let's see how can we do the relations and play with this transformation and apply and use, and can do some logic transformation to these relations. Okay, what can we do there? All right, it's gonna be fun today. So let's see an example here. All right. So here we have elements A and B, which are natural numbers, A and B. So A plus B. Remember the three parts? First, it's kind of the signature, declaration signature, and those forms signature. Okay, so first we tell you A and B are natural numbers. Then we give some constraint there. A plus B equals to 4. And then AB as a pair. We put a pair in this set. So this is a set after this EX. The whole thing represent a set. And so this is how we enumerate the set. It's 0, 4, 1, 3, 2, 2, 3, 1, 4, 0. Okay. Okay, 0, 4 and 4, 0. They are actually two different pairs. Okay. In terms of pair, if it's a set of 0, 4 or a set of 4, 0, that's actually the same set. But here it is a set of pairs. Okay, 0, 4 and 4, 0, different, two different pairs. In the pair, the order matters, but in a set, the order doesn't matter. Remember that. In a set, the order doesn't matter. Okay. So define the relation 0, 4, 1, 3. Because 0 plus 4 is 4. 1 plus 3 is 4. 2 plus 2 is 4. Okay. They are all natural numbers, and the sum of the pair is 4. That's why you put this. If you enumerate this A, B, and A plus B, 4 dot A, B, comma B. If you enumerate those list every element there, it's going to be something like this. Okay. So relations are usually named and can be written a number of ways. Here here's how we specify this relation. We define this relation. Okay. Here we define this EQ-less relation as we have two natural number, and we give some constraint there. So A equals B, and A is less than 4. So we kind of use this predicate calculus to kind of define a relation. Okay, so here is how we define the relation of a pair. All right. So here is how we enumerate them. So it's 0, 0, 1, 1, 2, 2, 3, 3. So the first way is more effective, because if it's really a small set, we can kind of enumerate all of them. It may be more efficient, like this one. However, if you want to represent some concept there, you would definitely want to go to the first way. You define the relationship. You just define the relationship with the predicate calculus. Okay. And here, if xy is contained in a relation, then say xy belongs to this R, or rxy. Okay. So if xy is a pair that contained in the relation R, this is what we can do. We can just say xy, this pair, belongs to R, or R brackets x and y, x comma y. So that means this pair belongs to that relation. Okay, so here, what can we say here? We can say 0, 0 belongs to equalist. 1 belongs to equalist. 2 belongs to equalist. Okay, so this is the name of the relationship, the relation. This is the relation itself. Okay, this is how we define the relation. This is actually how we enumerate all the possible elements there. But for most of the relation, we cannot just enumerate all. Yeah. Okay, so this is how we define the relation, right? There, how we define the relation. Be careful, there's 2 elements there, and we define the connection between those 2 elements. Okay, that's how we do with this relation. And here also something else. Here, because the equaless, we define the connection between the A and B, right? And A and B are all natural number. So we can say this relation is defined over natural number by natural number. It's defined the relation between a natural number and another natural number. So it's n by n. You will see that later. What is n by n and something else by something else. Okay, like a classroom by student, something like that. But here is a natural number by natural number. So the relations describe a relationship between the elements. The elements can be ordered pairs whose elements are sets. So here, let's see. What does that mean? So here we have 2 sets. Okay, files, new, old, archive, summary, text. And users, we have John, Roberts, Wilson. Okay, then we define a relation, which name is can access over the user by P, which is files. User by files. Okay, so what does that mean? We want to define the relation that the user can access the file. Okay, so there's like rights for every user. So not all, like you cannot access some secret files stored in the government server, right? So here we have this access control, kind of like access control here, which defines the relation over users by files. Okay, so which describes the files which in a particular user can access. So this could contain. So this is how we enumerate the relations here. Like Jones can access this new file. But Roberts can access the new, old, and summary file. This is yeah. Okay, this is still 2 things there, Jones and new. But this is Roberts. Okay, this is a pair of a object and a set of objects. Okay, so this is also legal here, because we mentioned here, we mentioned a little bit before. Relations describe relationships between the elements. Elements can be ordered pairs whose elements are sets. Okay. So we can have the relation define the connection between 2 sets. Right. But for the relation, it has to define the connection between 2 things, 2 elements. The connection between 2 elements. But these 2 elements, it can be some individual element, object, or it can be a set. Okay, but the relation still describes the connection between 2 things. Okay, but for each of the elements can be an individual object or a set. Okay, so that's clear. All right. So here, that's why we have Jones and a set of file. Jones can access and robots and a set of file robots can access. Okay, and Wilson and a set of file Wilson can access. But difference is this looks more like a set because it's more than elements there, more than one element there. Here it's also a set. It's a set of only one element. Okay, it's a set of only one element. All right. So this is a relation. Any question about that? Just a connection between two things, or a connection between two sets, or a connection between an object and a set, or a connection between a set of an object, or a connection between two objects. So that's all relations. Okay. And there are a number of operators defined for the relations. First is the domain operator, which can be written as a DOM, domain. And this operator, what it does, what the DOM operator does is it has only one operand, and its value is a set whose members are the left elements of the pairs in that relation. Okay, for example, here, for this can access, this Jones new, Roberts new old summary, Wilson text. For this set, we already defined as a can access. For this relation, we defined it as can access, remember? Here, can access is a relation over user by P. So this is that relation. Jones new, Roberts new old summary, Wilson text. This relation is called can access. That's how we name it. You can't name it anything, but we name it can access here. Alright. But if we apply the operator to this can access relation, the operator called domain operator, which is written as DOM. So this DOM can access is something you grab the left elements from all the pairs in this relation. Here, all the left elements for there is the Jones, Roberts, Wilson. So this DOM can access means Jones, Robert, and Wilson. Easy, right? Clear? So just the left thing. So there are a lot of pairs inside this relation. You grab the left thing here to form a new set that is DOM can access. All right. And we have another thing similar to DOM. We have a range operator. You can guess what it does. DOM grabs the left elements, and then range, it grabs the right elements. Okay. For example, here, given that user computer is the relation defined over user by computers, and this is a set of computer. It's VAX blah 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 sequent DRS 800. So that's the name of the computer, and the current value of use this computer. Use this computer is the relation between users and computer. It basically means who is using which computer. Like Jones is using the VAX computer, Roberts is using the sequent computer, Wilson is using the VAX computer. Okay, so the range, if we're doing this range to this relation, what's gonna happen is we grab the right hand elements, which is the computers. Okay, so range user uses computer is here. VAX 7800 and sequence. So why the DRS 800 is missing in this uses computer relation?
Because no one's using it.
Yeah, great. Because this range operator is applied to uses computer relations, and uses computer relations they are 3 elements. Specifies 3 persons using 2 computers. Okay, how 3 persons using 2 computers? So it only returns those 2 computers that is currently being used. So that's a range. Okay, so far so good. We all get the idea. Another thing is called inverse operator. Okay, remember DOM range, they are not very hard, right? DOM is left hand, range is right hand thing. We grab them to form a set. Straightforward. And inverse is also easy thing. So it's written as 1 as the superscript. Has 1 operand, which is a relation, the same as range and domain. It reverses the elements of the pairs of the relation it operates on. Okay. For example, given the use computer is a relation defined over user by computer, which is the same as above, and computer is this set VAX S DRS, and the current value of use computer is the same, Jones, Robot, Wilson. Okay, now we use this uses computer 1, which is the reverse. Okay, see here, inverse 1 as superscript, so it's an upper right superscript. The use computer 1 means we reverse. We reverse the Jones. Before the uses computer is Jones, comma VAX 8780. But if we reverse it, which means the order, we put it in the reverse order, inverse order. Okay, robots sequence Wilson VX. So it becomes VX, Wilson. Okay. Important thing here is that means in the pair, the order does matter. Okay. In a set, the order doesn't matter. The elements in a set does not have an order. Okay. But the elements in a pair, it does have order. Okay, remember that. Okay. All right. Let's try some. Use our hand. Let's do some exercise here. This is an example. Okay. So the OS users are classified by means of sets, normal users and privileged users. Okay, so there are 2 sets of users, 2 kinds of users, normal users and privileged users. The association between users and the files they own is modeled by a relation owns over users and the files. So what expression represents a set of files owned by privileged users? So take out your pen, grab a pen and piece of paper. Let's do this. Let's try this. It's okay if you cannot solve it, but it's important that you think about it. You think how you solve it. Okay. So let me remind you what we have learned It's a relation. What is a relation? Relation can be one object to another object, or set to set, object to set, set to object, something like that. And then we have three operators: domain, range, inverse, and then combines with whatever we learned whatever we learned for the predicates calculus. Can we define the privileged users? How can we define the privileged users? So the association between the users and the files they own is modeled by a relation. So there's a relation. We find the relation here, owns. The relation names owns over the users and the files. Users over files. Okay. So what we have now, let me make it more clear. What we have now is two sets. One set is normal users. The other set is privileged users. Okay. And then we have users and files. We have a relation. Relation is the users by the files. Okay. Now what we want to have is we use these operators and these relations to generate the expression that represents the set of files owned by privileged users. Okay. Okay. We have two sets and a relation already. We have two sets and a relation already. Now we want to generate another set, which is the files owned by the privileged users. Okay. What available is two sets and a relation. What we want to have is another set. Okay. It will be a little bit hard, difficult if you do this for the first time, but I'm sure you will get there after you try one or two questions. Generate a set from two set and a relation. Give you 2 more minutes. Okay. Come back. Okay. All right. So as I mentioned, what the question is asking for is a set, right? It is asking for a set. So we need to define a set for this question. To answer this question, we need to define a set. Still remember how we define a set? Like what I mentioned, we define a set with our maybe a declaration, and we has the separate, and a bar, a dot, right? Those things. We use those things to define a set, right? Let's see. And here we also play with. We have a lot of things available, and we play them with our operators. Let's see. The magic answer is here. Okay, let's forget about this for now. Now we have a set, right? This is a set. This is a set. This is a set. And we have 3 parts. The last part is omit. That's fine. But here is this. Okay. Here is in this set. This is a set. We have U and F. Okay, we have U and F. And it's a pair, U and F. Okay, where this U belongs to the privileged users, and UF, the relation between UF belongs to these owners. Okay, let's see how we reach there step by step. Okay, what the question asking for is the set of files that owned by privileged users. Some of the files is owned by privileged users. Some of the files are owned by general users. Now we want the set of file that is owned by the privileged users. Okay, let's see how we reach there. First, since we already have this relationship owns, which defines the ownership relationship. Okay, the ownership relationship. Okay, the ownership relation, which is between the U and F. The user owns the file, U and F. Okay. Now we have if we do not see this, we remove this. If we remove this range here, now this set is define the relation between the users and files. Between the users and files. Here, if we do not have this part, if only here, this first part, U, users, F, files, it defines the relation, everything between U and F, the users, files. Just a pair, every possible pair, U and file, okay, U and file. However, here, after this separate bar here, we this is just every possible pair between U and F. If we have 100 users and 100 files, then every possible, it's become a 10,000 possibility there. Okay. However, here we further put some limits, constraints there. So here we define that this users has to be a privileged users, okay, which may reduce that user number from 100 to maybe 10 of them. Okay, 10 of them. Okay, but if we think we have 10 users and 100 files, 10 by 100 still we have 1,000 possible pairs. Okay, after this end we put another conditions. Okay, so this UF relationship must belongs to this owns relation, which is defined there. Owns. Okay, so there are 10 privileged. For example, there are 10 privileged users, 100 file. Okay, maybe only 10 of them are belongs to this UF relation. Maybe it's a 10 by 10. Okay, something like that. Okay, so this actually defines, so this set, if we do not see this range, this whole set it actually defines the relation that privileged users and the files they owned. Okay, so it's a relation between privileged users and the file they own. Okay, and if we put the range here, we remove all the users, we have those files. Let me give you an example here. This may make it more solid. Okay, say if we have privileged users. Okay, John, Jake, Mark. Okay, so this is normal users. This is normal user, set of normal users. Okay, and then we have a set of privileged users. Which is, give me some name there. Give me some name.
Mark.
Mark. Yeah, Mark. Don. Par. PAT, Pat. Okay. We have 3 normal users in the system. We have 3 normal users and 3 privileged users. Okay, that's a set. Okay. Then we have a relation which is called owns, which means a whole bunch of pairs there. Okay. Whole bunch of pairs. All right. Let's, for example, pair 1, pair 2, pair 3, pair 4, pair 5, pair 6. Let's just do 6. Okay, 1, 2, 3, 4, 5, 6, 7. 7. That's fine. Maybe it could be a Pat owns file 7. Okay, and Jones owns the file 1. And Jake owns image 2. Mark owns audio file 2. Again, Mark owns file 5. Don owns image 2 as well. No, let's suppose we can own by only one person. Don owns the image 1, and at last, Jake owns file number 999. Okay. Okay, so we have a lot of files and a whole bunch of users. So that's what has been given. We have a set of normal users. which is Jones, Jack, and Mac. We have privileged users, which is Mark, Dom, and Pat. Now we have this owns relation here, which defines who owns what file. Okay, so here we know Pat owns file 7, Jones owns file 1, Jack image 1, Mark audio file 2, and also this Mark owns audio file 2 and also the file 5. So Mark can own many files, okay, and Dom on image 1, Jack on file 9. Okay, so what the question is asking for is a set of files that owns by P users, privileged users. Okay, so just by observing, tell me what are the set of files owned by the privileged users.
Audio 2.
Yeah, let's put it here. One moment. Let's audio 2, and file 5, and file 7, image 1. Okay, this actually makes it easier. The answer here, just this set. Let's say audio 2, file, image. It's easy. It's very easy for us to logically. It's very easy for us to pick all those files just by observation, right? Here, but if we are trying to define more formally, that's how we did here. You users, like, let me put it here again. If we define formally, it's gonna be first we have a set. Okay, we have a set in U and F. U is the users, F is the files. Okay, if we stopped here, this set is going to include all the possible combinations between users and files. Okay, some of the combination won't exist in this owns relation, right? Like Pat file 7 is in the owns. However, if you want to say Jones file 7, it doesn't exist anywhere in this own relationship. Okay, if we stopped here, this set will give you every possible combination between files and between users and files. Okay, and then we put more constraints there. Okay, first is still remember U belongs to, yeah, we want the privileged users file. Okay, so U belongs to privileged users. Okay, and that's not enough, right? And UF. Okay, if we stop here, every combination, then we put the one constraint there, it's gonna be every combination between privileged users and the other files. However, we want more constraints there because we want the actual file that owns by the privileged users. We do not want the files that owned by the general users, normal users. Okay, so then we put another condition, and UF pair belongs to this owns. So this set will give you the relation. Okay, the pair. Okay, this set will return you a whole bunch of set, a set of bunch of pairs. Okay, But in the pairs, the first element is the left-hand element is the privileged user, and the right-hand element is the file owned by that privileged user. Okay, if we stop here, that's the set we're getting. But the question is asking for files, so it's only asking for the files owned by the privileged user. So we put an operator which kind of extract all the right-hand elements from these pairs, right? So we put range there, ran. So this gives you actually the answer there. Okay. All right. It's kind of tricky the first time you did it, but once you get the idea, it's gonna be easier. Let's try another question. Okay. Let's try another thing. Okay. Now I'll give you two sets. Okay, now I'll tell you people on campus are classified by students and teachers. Okay, two sets. Students and teachers. I want to use this different. Okay, this is a set students and teachers. Okay, and okay, so the association between person and phone number. Person and phone number are represented as the phone number and the phone number represented as a relation called numbers. Okay. Right. Now let's see. We get make it. Okay, now it's a kind of different. We have three sets here. students, staff, and teachers. So people on campus are classified by students, staff, and teachers. The association between person and their phone number are represented as relation numbers. Okay. Now, how can we get the numbers of the staff, the set of numbers from the staff? Now, let's try to do it. 5 minutes? In 5 minutes? I don't think you need 5 minutes. It's pretty similar to whatever we just did. Let's try.
So it's going to be ran.
Can you write it down? Yeah. Write it down. So I want all of you to think about it. Yeah, do not look at the answer for the last question. Try to record that from your brain, in your brain. Do not directly look at the answer there. Like what we did is we define and further constraint, put some constraint there to finally reach the thing we want. Okay, let's come back. Alright, now I need a volunteer to write your answer on that whiteboard. Any volunteer? Please. it's okay if it's wrong. We can fix it. Yeah, you want? Thank you. Staff's
back and get my notes.
Yeah, I can let you know. So we need staff's phone number, right? We need the phone number of the staff.
It'd be something like that. Can I get my
Yeah.
computer to see what I wrote down again?
Okay. Just okay. Stop. Don't look at your computer. Just finish that part.
Alright.
Yeah.
This-
Then you will see the problem exposed there. You can fix it.
Oh, we need that.
Yeah. You almost make it.
There's something there.
Semicolon. Okay. So just one thing missing now. Only one thing is missing. Yeah. Okay. So here is the something belongs to some set.
Oh,
You need something.
person. Or no, phone number. Right.
Okay, so what is in the stuff? Persons in the stuff. So it's gonna be whatever you define as person. The P.
Okay. Oh, okay, that's right. He
Yeah.
exists. Okay. Alright.
It belongs to the stuff. And that P and phone number relation between the numbers. It's the numbers. Okay? Right. Great. So okay, just leave there. Yeah. That's fine. So you can make it without the notes. Yeah. So it's a person. So we have two things we defined. So because we know that we are given the relation, right? The person and his or her phone number. Okay, as numbers. So my number is 200, blah blah blah. Okay, and then we define the persons and the phone number, and we give because we only want the staff's phone number, so we want the person from this staff set, and we want the correct relation belongs to the number set. Okay, so that's how we define it here. I give you this set of students, staff, and teachers. The students and teachers, they are not used here at all because we only care about the staff's phone number. Okay, here. All right, so that's a little bit about how you play with this operators. They are a lot of fun. A lot of more fun we can have in Wednesday class. Okay. All right. So that's whatever we want to do today. All right. So thank you for coming. I'll see you on Wednesday. Do you feel you become actually smarter every Monday and Wednesday? All right. Thank you. See you.